Hello, welcome to Unit 5, Lesson 12, Reasoning about Exponential Graphs, Part 1. For this lesson, the learning objectives are: I can describe the effect of changing a and b on a graph that represents f of x equals a times b to the x power. And you will also be able to use equations and graphs to compare exponential functions. For time's sake, we're going to go ahead and skip the first activity and move on to activity 2. So in this activity, it says each of the following functions f, g, h, and j represent the amount of money in a bank account in dollars as a function of time x in years. They are each written in the form m of x equals a times b to the x power. The four functions are f of x equals 50 times 2 to the x power, g of x equals 50 times 3 to the x power, h of x equals 50 times 3 halves to the x power, and j of x equals 50 times 1 half to the x power. So for this problem, you're going to start off by first graphing each function on the graph. My recommendation is that you use Desmos. And when you enter in Desmos, just note that instead of using like f of x, g of x, h of x, and j of x, you're just going to use y every time, and the graphs will be different colors for each different function. Once you've graphed all four functions, you're going to go ahead and just make some observations about how when the b values change, how does that impact the graph. And just so you guys are aware, the b values would be 2, 3, 3 halves, and 0.5. Those are all b values. So go ahead, pause the video, and then once you have them graphed, make your observations and go ahead and start the video back up. Alright, so I took a picture of the four different graphs in Desmos. So if we look at that, the four different graphs, we have G is in blue, we have F in red, H in green, and then J in purple. So by looking at these graphs, we can see that where b is greater than 1, the larger values of b mean that the function grows more quickly as x increases, right? So g had a b value of 3, and that one is growing much quicker than f or h. F, which had a b value of 2, is the middle one, and then h, which had a b value of 3 halves or 1.5, is growing the slowest. We can also see that when the b value is less than 1, so j, for example, that's 0.5, that means that the function is decaying or decreasing as x increases. So let's go ahead and jot all of that down. Write it over here. Oops. Question 2 now has you looking at 3 new graphs, so P, Q, and R. They're still written in the same form, so let's take a look at those 3. So we have P of x equals 10 times 4 to the x power, Q of x equals 40 times 4 to the x power, and then finally R of x equals 100 times 4 to the x power. So in this case, my growth factor is the same every time, but notice what changes is our a value, right? That one's different each time. So go ahead, pause the video, graph these 3 lines, and then explain how changing the value of a changes the graph. All right, so I took a screenshot of what the graph looks like right here. So we can see the blue line, that represents equation r of x, which is 100 times 4 to the x power. We have the red line is q of x, which is 40 times 4 to the x power. And then finally, the black line, that's p of x, which was 10 times 4 to the x power. And what you may or may not notice is that by changing the a value is shifting the graph up or down. So for example, 100 is the biggest a value, and that one starts farther up on the y-axis, whereas the q of x, which had an a value of 40, that starts at the 40 on the y-axis. And then finally, p of x had a value of 10, and that starts on 10 on the y-axis. So changing the a value changes where the graph crosses the y-axis, sorry. So some key things to remember is that the a value of each function is basically the y-intercept. So the bigger the a is, the higher it is on the y-axis. Whereas the b value, this is more or less the steepness of the curve, right? The bigger the value is for b, the steeper it becomes because it's growing at a quicker rate. Note though that once you get to less than 1, it is no longer growing, it is now decaying. So it is, you should be able to quickly look at any exponential function and have an idea of what that graph will look like. It may not be perfect, but you should know A, where's the y-intercept, and B, is my my graph decaying or growing, and then finally you should have an idea of is it going to be steeper than a different graph, or is it going to be less steep? Let's go ahead and take a look at the next activity. So this next activity focuses on just exponential decay rather than exponential growth. The previous activity, we did mostly exponential growth. There was one decay equation in there, but all of these are going to be focusing on decay. So suppose you're presented with these four functions, M, N, P, and Q, that describe the amount of money in dollars in a bank account as a function of time, X, in years. If the account is yours and more money is better, which function would you choose and why? So the four functions are M of X equals 200 times 1/4 to the X power, N of X equals 200 times 1/2 to the X power, P of X equals 200 times 3/4 to the X power, and Q of X equals 200 times 7/8 to the X power. So again, we're all starting at that 200 mark. Every account starts with the same value, but you really need to determine which graph or which equation, which situation would give you more money, knowing that you're going to lose money either way. So for question 1, you're going to go ahead and start by matching each equation with the graph. You need to be prepared to explain how you know that. And then finally, question 2 says functions f and g are defined by these two new equations. Which function is decaying more quickly? And then you can go ahead and use your graphing technology to verify your response. So that's just a quick check. So go ahead, start with answering question 1. Once you finish question 1, rewatch the video and we can go from there. All right, so let's take a look at this. So if we remember what decay factor represents, remember it represents how much is left over, what's remaining. So for example, if a car loses 1/4 its value every 10 years or so, whatever, then we would say that 3/4 remain every 10 years. So we're talking in terms of money. We're saying that whatever the fraction is, that's the amount of money that remains each year. So keeping that in mind, we know that the bigger the decay factor is, the smaller the decay is. So looking at graph A, which has almost very little decay, right? It's almost actually a linear equation. We can see, though, that of the four, that one has the least amount of decay year to year. So that's going to match with my fraction that is the biggest. So that would be Q of X would go with A. B is next, right? So we look at the next biggest fraction, which is going to give me my P of X. Then we have C, which would go with the N of X, which has 1/2. And then finally, D would go with M of X, because that one is 1/4. So we can see that year to year, M of X has the most amount of decay because it excuse me, it has the least amount remaining each year. So now, knowing what you know about the first question, pause the video again and go ahead and attempt question 2 on your own. All right, let's look at question 2. So question 2 says functions f and g are defined by these two equations. F of x equals 1,000 times 1 to the 10th x power, and g of x equals 1,000 times 9/10 to the x power. So they're both starting at $1,000. Which one is decaying more quickly? So that means the one that is decaying more quickly is the one that has a smaller base because it has less remaining year to year. So that tells me that f of x is decaying more quickly. And our reasoning would just be it has the smaller base, so therefore there is less remaining each year. And when I say base, I'm talking about, in this case, the 1/10 is the base. Oops, I forgot the word base. You could go ahead and check this with a graphing calculator if you wanted to as well. So the question becomes, what if we had a different function, v of x, let's call it, and let's say if we had v of x equals 200 times 99 hundredths to the x power. What would this look like? So if we think about this, 99 hundredths tells us that that's a lot remaining from one interval to the next. So this tells us that it pretty much is very close to being a horizontal line or a diagonal line rather than a curve. Because nearly all of its values remain as x increases by 1. So this tells us it's decaying very slowly. It is an exponential function. 99 hundredths is not exactly 1. But if you were to look at it, it may not look like a curve. It may look pretty close to a straight line. And then vice versa, if we had v of x equals 200 times 1 over 100x, what would this graph look like? Well, this graph would go to 0 very, very quickly because it's losing a lot of its value as x increases by 1, right? Not much is left behind. So this is going to almost drop to 0 immediately, and then it flattens out over time. So just remember, so today we talked about when we have functions in exponential form, we have this standard form of a times b to the x power. We talked about how this represents the y-intercept, And b, this represents the growth of the function. We talked about when b is greater than 1, it is going to be a growth. And when b is less than 1 but still greater than 0, this is going to be a decay. That's it for this lesson. Thanks for watching.